visible spectroscopy. The radiations used in this case are UV and visible rays. Therefore, this part of spectroscopy is called as UV visible spectroscopy. It measures the energy absorbed when electrons in a molecule are promoted to higher energy level. The wavelength range used in UV visible spectroscopy are from 100 to 180 nanometers is called as far or vacuum UV region. So to use this range of wavelength, the instrument is designed to maintain vacuum. Hence this part of the spectroscopy is called as vacuum UV spectroscopy. The next region is from 180 to 400 nanometers. This is the usual UV region used for the study of the molecules. Then from 400 to 800 nanometer region is called as visible region. Sometimes along with UV region, visible region is also included in the study. Hence that part of the spectroscopy is called as UV visible spectroscopy. So what actually UV spectrum means? It is a graph of wavelength against absorbance or optical density. You can see the graph in this PPT. On the x-axis, the wavelength is plotted, and on the y-axis it is the optical density. And for one particular wavelength there is a maximum absorption, and that is called as Lambda Max. You can see here Lambda Max refers to the highest in the peak, and the corresponding wavelength is called as Lambda Max. Usually for explaining the spectra of the molecules, this parameter is used, that is Lambda Max. It is different for different molecules. Sometimes in UV spectroscopy, the wavelength is plotted against percentage transmittance because optical density is inversely proportional to the transmittance. Hence, percentage transmission is plotted along the y-axis and wavelength is plotted against the x-axis. So the range of UV radiation is from 100 to 180 to 400 nanometers. Why only this region is selected for the study of molecules? The reason is, you know, E is equal to h nu, where E is the energy, h is the Planck's constant, and nu is the frequency of radiation. If any wavelength is selected in this region, for example, lambda equal to 250 nanometers, if you substitute in this formula, then it will comes out to be around 500 kilojoules per mole. That means energy of 500 kilojoules per mole is sufficient to excite the electrons from bonding energy levels to the anti-bonding molecular orbitals. That is why the energy corresponding to the bonding energy in organic molecules, therefore absorption of UV radiation by molecule leads to the transitions among the electronic energy levels of the molecules. Hence this part of the spectroscopy is also called as electronic spectroscopy. And the theory behind this spectroscopy is Beer-Lambert's law. This law you have already studied in photochemistry in the lower classes. It says that absorbance is directly proportional to concentration and path length, or absorbance is equal to epsilon C L, where epsilon is molar extinction coefficient and C is the concentration in moles per dm cube and L is the thickness of the medium. So with the help of this formula, it is possible to calculate the epsilon, that is absorbance divided by concentration, when L is equal to 1 centimeter. Or the absorbance from the Beer-Lambert's law, it's equal to log of I naught by I, where I naught is intensity of the incident light and I is the intensity of the transmitted light. So from these two equations, we can conclude that log of I naught by I is equal to epsilon CL. So this is the basis of the principle lying behind the UV spectroscopy, in which absorbance is plotted against the y-axis and corresponding to the wavelength on the x-axis. So now we shall see what is electronic transition, and this is the important aspect in the study of UV spectroscopy, because the UV radiations which are used in the study of molecules are just enough to cause the excitation of electrons from ground level to the higher energy level. And this electronic transition includes the following transitions. So you can see from this figure that in the lower classes you have studied regarding the molecular orbitals. During the formation of the molecules, the electrons are shared between the atoms and they form the molecular orbitals. Hence, the electrons which are there in a molecule are in the bonding orbital, and this bonding orbital may be a sigma bond or pi bond or the non-bonding electrons. So according to that, the electrons present in sigma bond are called as sigma electrons, the electrons present in the pi bond are called as pi electrons, and the one which are not involved in bonding, like the one present on oxygen or nitrogen, they are called as non-bonding electrons. And all these energy levels are in the ground state, or the energy corresponding to these orbitals is less. And along with molecular orbitals, there is a formation of anti-bonding molecular orbital also, and they are designated by phi star and sigma star. Among these two, phi star antibonding energy level is having lesser energy than the sigma antibonding molecular orbital. And if you compare here, the sigma bonding electrons have got the less energy than the pi bond than the non-bonding electrons. So this is the energy distribution with respect to the electronic energy levels in a molecule, and these three are called as bonding molecular orbitals and these two are called as the anti-bonding molecular orbital. Since the non-bonding electrons are not at all involved in the bonding, there is no anti-bonding energy level corresponding to this. So usually in the molecule, the electrons will reside in the ground energy level. When a molecule absorbs UV light, UV radiation, any of these excitations are possible corresponding to the nature of the electron present in a molecule. For example, if the UV radiation is responsible for causing the excitation of electrons from sigma bonding orbitals to sigma anti-bonding molecular orbital, that kind of transition is called as sigma to sigma star electronic transition. That is, the compounds such as methane or alkanes, which have only sigma bonds in a molecule, no pi bond and no non-bonding electrons. Under such circumstances, if the UV radiation is absorbed, and that will cause only the excitations of sigma electrons to sigma star antibonding energy level, and that is called as sigma to sigma star electronic transition. And usually this kind of electronic transition requires high energy. Therefore, you can see from this figure, it requires higher energy. UV radiation range corresponding to 100 to 180, that is vacuum UV region, is used for the study of this kind of the bond present in a molecule, and it requires sophisticated instrument, and usually they are not studied under UV spectroscopy. Then we have the molecules such as ethyl alcohol or ethyl amine, the amines. So in such cases, the molecule contains the sigma bonds. Along with that, these atoms, oxygen, nitrogen, sulfur, will have non-bonding electrons. Hence, these kinds of molecules, when they absorb light, they can bring about the excitation of electrons from non-bonding energy level to sigma star antibonding energy level. Hence, it is called as N to sigma star transition. That is, what do you mean by N to sigma star transition? It is the excitation or transition of non-bonding electrons to sigma star antibonding molecular orbital. So this will happen in case of molecules which contain non-bonding electrons. Along with that, if there are sigma bonds, and this transition usually needs less energy than the sigma to sigma star electronic transition, and the wavelength range which will bring about this transition is from 150 to 250 nanometers. Next is very important kind of transition called as pi to pi star electronic transition, and this kind of transition happens in molecules containing pi bonds. See, all alkenes, carbonyls, nitriles, aromatic compounds, they exhibit the pi to pi star electronic transition. Hence, what is pi to pi star electronic transition? It is the transition or excitation of electrons from pi bonding molecular orbital to pi star anti-bonding molecular orbital, and this is called as pi to pi star electronic transition. And this kind of electronic transition, that is excitation, will occur in molecules containing double bonds, that is unsaturated molecules, and this will occur in the wavelength region from 170 to 205 nanometers. Then comes N to 5 star electronic transition. So it is the excitation of non-bonding electrons in the non-bonding energy level to 5 star antibonding molecular orbital, and this will occur in the compounds containing both double bond and heteroatoms which contain non-bonding electrons. And N to pi star transition requires minimum energy, and it will occur around the wavelength 300 nanometers. So to sum up this, there are mainly 4 types of electronic transitions, and this will occur when the electrons in these molecular orbitals, that is bonding molecular orbitals, when they excite to anti-bonding energy levels. So depending on the state in the lower energy level to the higher energy level, they have been classified as sigma to sigma star electronic transition, pi to pi star electronic transition, then n to sigma star electronic transition, then last one is n to pi star electronic transition. So I will repeat, what is sigma to sigma star electronic transition? It is the excitation of electrons from sigma bonding molecular orbital to sigma star antibonding molecular orbital, and this requires higher energy. Second one is pi to pi star electronic transition, which is nothing but the excitation of electrons from pi bonding molecular orbital to pi star antibonding molecular orbital, and this will occur in the compounds containing unsaturated bonds. Next comes N to sigma star electronic transition. That means excitation of the non-bonding electrons to sigma star antibonding molecular orbitals. Then the last one is the excitation of electrons from non-bonding energy level to pi star antibonding energy level. So these are the four different types of electronic transition which will occur depending upon the kind of electrons present in a molecule. So with this, I will conclude today's topic, and the next I will take up in the